Okay, so we'll start with the same problem that we have discussed, and we have designed the main member, that is 2 ISLC 350, and its spacing is clear spacing, which is clear spacing of 22 centimeters. Okay, for the same problem, that is design load is 12 kN, effective length is 8 meter, effectively held in position at both ends, but restrained against rotation at one end, and Fy value was 250 MPa with a 20 mm dia power division device. Okay, so our column design is over. Our remaining part is the design of the tie members, which are basically lacing and the buttons. Okay, we'll start the design of lacing part first. Okay, now there are two things are there. Either you can design with a single lacing systems or a double lacing systems. You have to assume which one you want, whether you want single lacing system or you want double lacing system. Let us say I am doing here a single lacing system. So assume a single lacing system. Now you know what is the angle of lacing. Okay, that you have to decide once again. So let us say I am deciding an angle of lacing of 45 degree. This value range between 40 to 70 degree. If you remember, I said in the last class that this value will range between 40 to 70 degree. So since it is 40 to 70 degree, I can take anything in between that. So I am taking, say, the angle is 45 degree. Okay, so my assumption is assume a single lacing system with an angle of lacing 45 degree. So if I do that assumption, how will it look? Just to a rough sketch. So this is the vertical column member. Okay, so this continuous one. So this is column member. Okay, and my lacing, single lacing system I am doing. Assume this is approximately 45 degree. This direction, then of course you can go in this direction also. Fine. Similarly, it is a continuous process. So what I have done is I have done with an assumption that this theta is 45 degree. This is 45 degree, means this is also 45 degree. Our assumption is that this spacing is, we have just calculated that we are giving a spacing of how much? 220 mm. Okay, since we are using a ISMC, what was that? ISLC 350 was used, right? So what we have to find for ISLC 350, what is the B value that we have to check? Okay, for ISLC 350, let me check that from the steel table. For ISLC 350, this B value is 100 mm. Fine. For ISLC 350, the B value, this value is 100 mm. Okay, and CYY already I have written earlier. That was how much? 24.2 mm. 24.2 mm. Fine. So let us assume that I am using a single line of the rivets. It may be more than that with these systems. Okay, and approximately say this is here. So say approximately from here to here, or from here to here, this distance is approximately, we are using 60 mm. Okay, 60 mm. So what is this total total from here to here, total from here to here is coming how much? 340. Sorry, it's coming 300. It's coming 340 mm. Our job is to know what is this length. This is basically what? L. Right? This is the L. So can we find out that L? This L, it is center to center spacing of the lacing bar is equal to, if this distance is known to us, how much? 340. What will be this distance? This is nothing but if it's just a rough sketch. If I draw this line, then what I get from here to here, this is known to me. So what will be from here to here? It will be same, because this angle is 45 degree. So this will be just double of this. So simply you can write, or what you can do, you can write down, see this is base, this is perpendicular. So this will be L by 2. If you take this triangle, in terms of triangle I write L by 2 is equal to, what is that? 1045. 1045 degree of the base of this triangle. That means what? L is equal to 2 times the base. What is the base of this triangle? Base of this triangle is 340. 340 and 1045 is how much? 1. So this is coming how much? 680. Okay. So by this geometry we are getting that the spacing should be 680 mm or 68 centimeter. Both you can write 68 centimeter. Okay. Next. So this we got 680 mm. Fine. What is the next job? Our next job is to find out the, check it whether it is satisfying the Kudal provision or not. What is the Kudal provision? Kudal provision is that L divided by RC minimum. L divided by RC minimum should not be more than, what was that? 50. Should not be more than 50 or 0.7 times the slenderness ratio of the column. Okay. So RC minimum means for the column member, what is the minimum radius of gyration? Individual column member. So if you go to the steel table, for the column member, individual column member, that is individual channel section, is nothing but this will be RYY, and this value is given in the code book as 28.3 mm. Okay, so L divided by RC minimum is equal to L how much? 680 divided by 28.3. Okay, this is coming out to be 24.03. So 24.03 is, first of all, it is not more than 50. Okay, second times you check with 0.7 times of the slenderness, maximum slenderness ratio of the column. It is 0.7 into, if you remember the previous lectures, we have found out what is the slenderness ratio, maximum slenderness ratio of this section, and what was that value? That lambda value we have calculated was 46.65. 46.65. Okay, so 0.7 times of 46.65 is also more than 24.03. So this is once again not more than this. That means whatever we can say, this is satisfying. There is L divided by RC minimum is not more than 50 or not more than 0.7 times 46.61. That means whatever the L we have assumed is correct. That means L equal to 680 is accepted. Fine. Now what we will do, we will go for finding out the thickness and the breadth of the member. This is fixed. Okay, now come to the next part. Effective length of the lacing bar. So what is this length? First find out. From here to here, center to center space. What will this length? This length is how much? 340. So write down. Effective length of lacing bar, say LE, or otherwise depends simply effective length of. So I am writing effective length of lacing. Effective length of, say, lacing bar. Okay, so if you say this is L, then what I can write? This is base. This base of this triangle is 340. This is hypotenuse. So simple, what I can write? 340 divided by the hypotenuse. Hypotenuse of this triangle is equal to what? If this is 45 degrees, this is also 45 degrees. So sin 45 degree. Right, sin 45 degree is how much? 1 upon root 2. So LE, that is effective length of the lacing bar, is nothing but equal to 340 root 2 millimeter. Fine. What is the minimum thickness for a single lacing system? T minimum thickness should not be less than LEL by 40. Just you refer the previous lecture where I have discussed what should be the minimum length of a minimum thickness, and it is saying that T should not be less than LE upon 40. So in this case LEL is how much? 340 root 2 divided by 40. If you calculate it, this value comes out. This value comes out approximately 12 mm. Okay, this value is coming little bit less than 12 mm, so we can take up to 12 mm. Okay, so thickness of this thickness we are taking as 12 mm. Then what we have to choose? We have to choose the breadth. This breadth depends on the diameter you are using. Since in the problem I said use 20 mm diameter, or you can decide your own if it is not given in the problem. For 20 mm diameter rebate, the breadth of the lacing bar is to be taken as per the given table or cookbook guideline is to be 60. Okay, so the breadth of the lacing bar we are taking as how much? 60 mm. Fine. And the thickness of the lacing bar is decided as how much? That is 12 mm. Okay, so I am writing here this B we are taking 60 and T is taken as 12. Okay, remember this breadth how we have taken? We have taken the cookbook's guideline that for depending on the different diameters. Okay, so that means finally we can say we are using a lacing bar of 60 by 12. Okay, so everything with 20 mm dia, power division rebates. Okay, using a 60 by 12 20 mm dia power division. Now let us check what is the maximum slenderness ratio of the lacing bar. If you just see the last class or last lecture, we have said that maximum slenderness ratio is what? L effective divided by radius of gyration, and that we have derived as that is equal to L effective root 12 divided by the thickness that we have calculated. And as per the Kudal provision, this value should not be more than 145. Let us check what happened in our case. In our case, effective length is how much? 340 root 2. 340 root 2 multiplied by root 12 divided by 12 mm. Calculate this value comes out around 138.8. So 130.8 is less than 145. So we can say from the standardness point of view, this is also accepted. Once we know this value, then what we can do? We can find out the sigma SC, this is permissible compressive stress of the lacing bar. How to find out that? For that, you go to the IS code to refer table number 5.1, find out the for lambda value 130 and for lambda value 140. Check what is the sigma SC value. We are using Fe 250 still, so if you check that, this value is given 57 and as per my book this value is given as 51. So if you do the interpolation between these two for a lambda value of 130.8, the sigma SC value for lacing bar is coming out to be 51.72 MPa. Okay, now we have to check that whether our design is safe or not. For that, okay, just simply I am writing this value somewhere here, that sigma SC for lacing bar is 51.7. okay, now go to the next part. Next, just for checking purpose, what we need to know what is the design shear. So design shear or the transverse shear on lacing bar B is what we said last class. Our last lecture we have discussed that as per the code book, this value is 2.5%. 2.5% of the given load. 2.5% of the given load. What is our given load? Our given load is 1200 kilonewton. So this value is how much? 30 kilonewton. Okay, so force on each lacing bar. Last class we have found out that F is equal to design shear divided by 2 into sine theta. Here theta means 45 degree. 2 into sine 45 degree. Put this value here 30 divided by 2 into sine 45. Calculate that F value is coming 21.21 kilonewton. Now it may be compressive one or it may be a tensile one. We do not know which direction it is. So let us assume that it is a tensile tension. If you assume it is a tension, then what is the tensile stress that we can calculate? For a tension bar, the tensile stress, maximum tensile stress is what? Force divided by net area. Force divided by net area. Okay, here how much is the force? Our force in a member is 21.21 kilonewton. So 21.1 into 10 to the power 3. Net area, assuming a single repeats. So what is the net area? Net area is coming out as 60 is the breadth minus what is the diameter of the rivet? Diameter of the rivet 20. So this will be 21.5. That is the gross diameter multiplied by the thickness of the lacing bar we have taken as 12. Sorry. So what is this value? This value is coming out 45.9 MPa. This must be less than sigma T. Sigma T is how much? 0.6 Fy. 0.6 Fy. Fy is 250. That means sigma T is how much? This is 0.6 6 into 250, and that means this value is less than 150 MPa. 150 MPa. Okay, and we got a value of less than 150 MPa. That means from the tension point of view, our design is safe. Next, we have to check the compressive stress. What is compressive stress? Compressive stress is equal to force divided by gross area. So compressive stress is equal to force divided by gross area. Okay, what is our force here? Force here is 21.21 kilonewton. And what is the gross area? Gross area is cross-sectional area of the lacing bar is 16 to 12. This comes out how much? 29.46 MPa. Okay, this must be less than the value of sigma S. How much sigma S we have calculated? Just go back, or you can see here it is written as 51.72. So this value is coming less than 51.72. That means what we can say that our whatever the lacing member we have decided, this lacing member is safe in compression points of view. So it will not fail in tension, it will not fail in compression. Okay. So lacing bar is decided. Now our next job is to design the end connection. How many rivets are required and what are all those things? That let us use quickly. For design of end connection, what is it? Initially we said that we are using 20 mm dia power driven rivet. So we have to find out the rivet value. To find out the rivet value, what we need? We need to find out the strength against shear failure, and we have to find out the strength against bearing failure. Strength against shear failure is how much? 5/4 d square into tau bf. Tau bf for a power driven rivet is how much? Already I have discussed earlier. This value is 100. So if we use this here, you will get this value as 36.3 kilonewton. What is the gross diameter for 20 mm rivet? That is 21.5. So use here 21.5 and tau bf is 100. Convert into kilonewton. This value comes out as 36.3 kilonewton. What is the next part? Next is the bearing stress. Bearing stress PB is equal to, what is the equation? Equation is D into T into sigma PF. So D into T into sigma PF. Right? What is the D here? D here is diameter of the gross diameter of the rivet is 21.5. It is 21.5. Thickness of the section is 12, and sigma PF for power driven rivet is 300. So if you multiply this, it is 300. Okay, if you multiply this value is coming out to be 77.4 kilonewton, right? So PS is 36.3, PB is 77.4. That is strength against shear failure is 36.3 kilonewton. Strength against bearing failure is 77.4 kilonewton. So what is the rivet value? Rivet value, we know that rivet value is the minimum of these two. So what is the minimum of these two? Minimum of these two is 36.3. So the rivet value here is equal to 36.3 kilonewton, right? So we got the rivet value. Now once we know the rivet value, then what we can do? We can find out the number of rivet. So number of rivet. Number of rivet, if you remember the last class, it depends on the arrangement, which category of the arrangement we are using in the problem. Based on that we can find out the rivet value. In this case, if you look at this case, and if you look at the previous discussion, this is category 2. In such cases, the rivet value is calculated as 2f. Number of rivet is calculated as 2f cos theta divided by the rivet value. In our case, what is f? F is 21.21. So 2 into 21.21 into cos 45 divided by the rivet value. Just now we have calculated as 36.3. So calculate this, and this will give you the number of rivet required. Plus cos 45. So the number of rivet required is coming very close to 1, little bit less than 1. So that means what we can say is 1. That means what we are doing, finally we are providing single lacing system of lacing bar size 60 mm, flat lacing bar of size 60 mm by 12 mm with inclined at an angle of 45 degree and connected by 20 mm dia power demand rivets at each end. Okay, single 20 mm power demand rivets. Okay, so that's the design of the lacing bar. Then we have to design the battens. Okay, let's start the next part. Okay, so see the problem, I can design it using the lacing system or I can design it using the batten system. Lacing system I have done. Now the same problem can be solved by batten system. That means we will not provide the lacing bar, rather than we will provide the battens. Okay, so if the batten is to be provided, so what is to be done? So that's why I am designing the batten. Okay, don't be confused. Any one of them, either you use lacing or use batten. Okay, let us see how we can provide the batten. Okay, we know that whenever a column is designed with battens, the effective length of the column is to be increased by 10%. So the effective length of the column, now the new effective length, say LE1, will be equal to 10% increase, so 1.1 times of 0.8 times of the original length of the column. This comes out 7.04 meters. Okay, effective length is 10%. Okay, let us do one thing. Let us start this batten column in a different lecture because it will take time. In this case, because earlier what we did, we have designed the column, we have designed the lacing. So that was the lacing column. Now we have to design the batten column. So again we have to design the column as per the requirement because effective length is changing, and again we have to design the batten. So let us do in a separate lecture. Let us stop this lecture here itself. Okay, stop it.